everybody, this is Mrs. Hanson, and today my goal is to help you guys with adding strong acid or strong base to a buffer solution and how to handle those mice tables and then how to handle the ice tables after that. So in class we had gone through some examples, but I really want to walk through very carefully the last two examples, which are letter E and I think letter G in your notes. So in this particular example we had just started in class, but we're going to finish it now. So the basic idea is that instead of adding strong base, this time we're adding hydrochloric acid, 50 mils, to the same buffer solution. So first of all, you got to decide, okay, if I add strong acid, what part of the buffer is going to rise to the challenge and go ahead and eat up that strong acid, that H+. So of course, H+ is going to react with the base part of the buffer. So H+ is going to react with the ammonia, and the ammonia is going to do what the base does. It's going to consume that H+, so you don't get a big pH change, and you're going to make some more of that conjugate acid. So for the mice table, first thing you got to do is get all these quantities into moles. So the basic difference between the ice table and a mice table is that the mice table is based on moles. So we'll go ahead and record the volumes and the molarities for each of these respective solutions. So for my HCl, we had 50 milliliters, and it was 0.05 molar. Okay, and for the NH3, it was part of the buffer solution, which we had 80 milliliters. And the NH3 was 0.3 molar, and the NH4 plus was 0.36 molar. So when it's all said and done, here's what my mole values look like. All right, so thinking back to last year chemistry, this is a classic limiting reactant problem. Anytime you add a strong acid or a strong base, the reaction goes to completion. So in this case, what am I going to run out of? The H+ is the lowest quantity, so that's my limiting reactant. So the H+ is going to be totally consumed. For the next row, that's my change in moles. H+ totally gets used up. The NH3 goes down by that same amount, 0.0025, and then the NH4 plus goes up by the 0.0025. I will tell you that this is one of the most common mistakes, that people just go crazy with the subtract, and then they subtract again. But if the H+ and the NH3 both go down, then the NH4 plus has to go up. All right, so these are my final mole values. Of course, the H+ is 0. NH3 went down just a little bit, NH4 plus went up. Before you can move on, you want to get those mole values into concentration. And that's where you want to be careful, because you had an additive solution. You added 80 mils of the buffer solution to 50 mils of the HCl. So the new volume for the solution mixture at the end is 130 mils. So you want to divide by 0.130. All right, so there's my final molarities at the end of the mice table. So here's the thing. You know what? I added that strong acid. The reaction went to completion. I am no longer at equilibrium. So it's kind of like Le Chatelier's principle all over again. We've created a stress on the system. So guess what? The system is going to have to re-establish equilibrium. So hopefully, when you think about re-establishing equilibria, that makes you think an ice table. And you would be absolutely correct. Of course, we talked about in class the simplification of that ice table, a trick, if you will, is that if you do still have a buffer situation, you can use the Henderson-Hasselbalch. Sorry, I'm coughing in your ear. Okay, so do we still have a buffer situation? Let's see. We have weak base present, and we have conjugate acid present. We have both components of a perfect buffer. So go ahead, give it a go, see if you can use the Henderson-Hasselbalch. I would try it, and then I'll go ahead and flash up the answer. So you're working, right? You're trying it out. So did you get 9.18? I hope so. So pH for the Henderson-Hasselbalch equals pKa plus log of base over acid. And it doesn't matter that this is a base buffer, meaning that you're using the weak base ammonia. Still, we're looking for pH. So it's pH plus a pKa. So make sure that you do get the Ka value, not the Kb value. So you had to convert it, plus log of base over acid. You can probably guess that this is a really common mistake too, is to get those mixed up. So you look very carefully at your mice table. My base is now the 0.17, and my NH4 plus is now the 0.24. All right, 9.18. All right, just to reiterate, there's a lot of different ways to skin a cat, as they always say, so there's different methods you can use. Please remember, anytime you're using the Henderson-Hasselbalch, you're really just doing an ice table. So I know the ice table takes more time, but if I ever ask for it, you should be able to justify the Henderson-Hasselbalch formula with an ice table. So that's what I pictured down here. So the NH3, same base dissociation reaction that we started with. This is never going to change. But what did change is the initial values, because after I added that strong acid, equilibrium was all messed up. So I had these new values. These came straight off that mice table. And then we're going to shift. We're going to reestablish equilibrium. So this guy goes down, these guys go back up, and then now you can just solve. But keep in mind that this was a weak base, so I have OH minus over here. So I needed the KB value, and then you guys could solve. And it was pretty easy. The minus X and the plus X, of course, disappear. But that X value represents the hydroxide ion, right? And then you can solve for the POH, the negative log of that number, and you get the pH. And a third method you could use, you can always solve for pH. I suggest that totally, but yeah, you could solve for POH as well, which might make more sense with the base situation. But POH equals PKB plus log of acid over base. So it's basically the exact same thing, but adjusted or opposite for a base situation. I mean, when you solve, everything's totally fine, except you do have to make sure that you convert the POH back to pH. So when it's all said and done, of course, I'm going to suggest that this is the best method because it's simplest and it's easiest. But I do want you always to remember that if you're using the Henderson-Hasselbalch formula, you're really, in a very quick fashion, setting up an ice table. So you just, every once in a while, you might want to kick it back old school and set up that ice table. Make sure you get the same answer. All right, the last part, super simple. All you're doing is proving that a buffer does buffer. So this time, instead of adding that 50 mils of acid to the buffer solution, you're just adding it to pure water. So really, hopefully you're just thinking about this as a typical or a classic dilution problem. Meaning you had 50 mils of the acid, and now you just added 80 mils of water, so you diluted it. So M1B1 equals M2B2, and the pH comes out to 1.72. So that's what would happen if you just added the acid to normal water. Going back to the problem we just did, just a little FYI, the pH was 9.11. If you go back to our original buffer solution, if you flip over a page, the original buffer was 9.18. Okay, I don't have the word for that. That's fine. So the original buffer was 9.18. By adding the strong acid, you went down to a pH of 9.11, which totally makes sense because if you go back up to your mice table, by adding the strong acid, you consumed some of the base part of the buffer, and you made some additional amount of the acid part of the buffer. So your solution overall got slightly more acidic. All right, well, I hope that helps. I hope you feel really comfortable with mice tables, and then what you do with that afterward using the Henderson-Hasselbalch. All right, don't forget, check out that second video, which will finish up the notes. You guys have a wonderful day.